Duygu Hocam günaydınlar.
Günaydın. Günaydın
Bakalım,
hocam.
bakalım sesimden beni tanıyabilecek misiniz?
Aha, İbrahim hocam sizsiniz. İsminizi gördüm. Nasılsınız?
Eyvallah. İyiyim hocam, teşekkür ederim. Merhabalar, siz nasılsınız?
İyiyim, çok teşekkür ederim hocam. Oraya gelemedim, malum Çorum'dan katılıyorum.
Olsun, sağlık olsun hocam.
Kusura bakmayın, çok isterdim orada
Estağfurullah.
olmayı.
Estağfurullah. Birkaç dakikaya başlayacağız hocam, olur mu?
Tamam hocam, nasıl isterseniz.
Hello. Good morning from the İCMATSE 2024 Saturday Holby İstanbul, the morning session. We will start our presentation with Ms. Duygu Candemir. His presentation entitled with Dual Dot NCZAZ cathode material for lithium-ion batteries. So, can you hear me, Ms. Candemir?
Yes, I can hear you.
Okay. If you are ready, you can share your presentation
Yeah,
screen.
okay.
Okay. Now we can see your screen. When you're ready, you can start.
Okay, I'm ready. Start. Um, Hello, dear chairmen and dear participants. I'm Duygu Candemir. Welcome to my presentation. Today, I will tell you about a small part of my PhD thesis under the title of Dual Doped NCZAZ cathode material for lithium-ion batteries. Before presenting my analysis results, I would like to share with you some brief information about lithium-ion batteries. Devices that convert chemical energy into electrical energy and store it all are called batteries. Batteries are classified into two categories, non-rechargeable batteries and rechargeable batteries. Common examples include lead acid, nickel cadmium, lithium-ion and lithium polymer batteries. In our century, almost everyone has a portable electronic device. A portable energy source is a basic requirement for using these wireless devices. For this reason, batteries are widely used to meet the energy needs of portable electronic device technology. Lithium-ion batteries are recognized as the most energy-dense secondary batteries available. Lithium is the most electropositive element and the lightest metal, which makes it ideal for designing high-energy systems. As battery technology advances, various types of lithium-ion batteries have been developed, each with unique properties. These batteries can operate at higher voltage, have a lower memory effect, and last longer than other secondary batteries. As a result, they are widely used in devices such as mobile phone, laptops, tablets, and hybrid vehicles. So, what's inside a lithium-ion battery? The components inside all lithium batteries are essentially the same. Here we see the layers of the CR2032 type lithium-ion battery. This battery is commonly used in laboratory scale studies and consists of a cathode, separator, anode, spacer, and wave spring, arranged between top and bottom covers. A liquid electrolyte inside the battery provides conductivity and facilitates the movement of lithium ions. The cathode base and anode top serve as the contact point for the current. In the study, we focus on the synthesis, characterization, and development of the cathode materials. The anode and cathode, just I mentioned, play the main role in the battery. The entire energy conversion mechanism is related to the travel of lithium ions between these two electrodes during charging and the discharging and use of the battery. Energy conversion in lithium-ion batteries occurs two ways, as charging and discharging. During the battery charging process, the external and electronic current separates lithium ions from the cathode. These ions then diffuse through the electrolyte and move in the structure of negative anode. At the same time, electrons released from the positive electrode travel to the anode. Anode. At the same time, electrons released from the positive electrode travel to the anode via the current conductor cable. During discharge, the lithium ions that have moved to the anode return to cathode, transferring the energy stored in the electrons. We can see the lithium movement more clearly in this simulation. Here is cathode, here is anode. Charging. And discharging. Okay. Lithium metal oxide refers to a type of intercalation compounds. In a battery with a light structure, lithium transition metals and oxygen are arranged in the two-dimensional layers. As shown in the figure on the right, the structure alternates between a lithium layer, an oxygen layer, a metal oxide layer, and another oxygen layer, followed by another lithium layer. When lithium is removed, the framework must remain unchanged to maintain neutrality. When a lithium ions is removed from the cathode, is carries a positive charge. This is where the transition metals in the cathode plays a crucial role, as they compensate for the charge when lithium ions enter or leave. Therefore, when doping is done to change the properties of the cathode materials, the chosen element is typical transition metal that can change its valence to help maintain neutrality. If the structure changes, it becomes very difficult to reintroduce lithium. In addition to the previous role of additive elements, they also have an important place in maintaining the stability of the structure. The electrolyte used in lithium-ion batteries decomposes during cycles, forming an electrolyte interface, that means SEI, which disrupts the stability of the structure and significantly affects battery performance. In addition, oxygen release from the cathode material during cycles causes the formation of water and carbon dioxide in the electrolyte. The resulting water hydrolyzes the lithium hexafluorophosphate salt in the electrolyte, resulting in the release of HF and phosphoryl fluoride. This HF dissolves the transition metals in the cathode and causes a decrease in the active material. This cycle continues until the battery becomes inoperable. Therefore, it is desired for the structure to be stable as possible. And such problems are largely prevented with the appropriate additive elements used. In this study, we solved the problems I mentioned. We synthesized the cathode material by dual doping the starting hydroxide powder containing nickel, cobalt, zinc with an aluminum and zirconium via solgel-assisted solid-state doping method. Research showed that the doping of aluminum transition element reduces cation mixing and improves the structure and thermal stability of batteries, while zirconium doping enhances cycling stability and increases specific capacity. Moreover, co-doping with aluminum and zirconium minimizes cation mixing and microcrack formation by creating synergetic effect. After producing the cathode powder, we first applied XRD and retrieval requirement analysis to determine the crystal lattice structure of the material. When we examine the XRD spectrum, we see all of the peaks exhibit a similar diffraction pattern with the hexagonal layered structure. The separation of the 006 and 102 and 108, 110 peaks marked in a spectrum represent a well-ordered layered structure. This indicates that the dopant elements are correctly integrated into the structure without disturbing it, allowing for this easy entry and exit of the lithium ions during charging and discharging. The ratio of the 003 and 104 peaks intensities is an important criterion of cation mixing. The acceptable minimum value is reported as 1.2. This value was also calculated in the study, 1.2 for this material. Moreover, the C divided by A value obtained by retrieval requirement analysis is related to the degree of trigonal distortion. When this value is higher than 4.899, it means that higher cation ordering and low cation mixing are obtained. In our results, this value was found to be 4.955. In addition, it can be stated that lithium layer spacing, which facilitates lithium intercalation during the charge-discharge process, is also ideal range. Some images of the starting material and cathode material, starting material here and cathode material are given in this picture. When the images are examined, it's clearly seen that spherical form is not distorted after doping and calcination process. And the cathode material consists of secondary particles surrounded by primary crystals and nanometer scale. This situation is evidence that crystallization has occurred completely. The cross-sectional linear element analysis EDS of the cathode materials is shown in this picture. When the resulting spectrum is examined, it's clearly seen that the analyzed graphs of the elements continue homogeneously and throughout the grain. This can be accepted as an indication that aluminum and zirconium elements are incorporated into the structure homogeneously throughout the particle after calcination. As a result, when we analyze the data from the XRD spectrum, Rietveld analysis, and SEM EDS, whose importance was explained earlier, we found that the doping elements were successfully integrated in the structure. In this study, which is carried out within the scope of the PhD thesis subject, studies on determination of different temperature, different composition, and electrochemical properties are ongoing. Thank you.
Okay. So thank you very much for your warm presentation, Ms.
And
Candemir.
thank you as well.
Your presentation have many useful information, I think, for the electrical vehicles issue.
Thank you.
So I want to ask my hall, is there any question? No. Okay, there is no question, Candemir. Everybody understand very well from your presentation. Thank you very much. You can stop your sharing and see you next time, inshallah.
Inshallah. Thank you.
Okay. Okay, bye-bye.
Bye-bye.
So, and our next speaker, Arap Loiza, you are here. Okay, we are waiting your presentation. I think, will you give some? Okay, I can give that. Okay.
Wait, yes, here, please.
This one?
Yeah.
This.
Okay.
Okay, I want to announce again, our next speaker is Arap Loiza. She is here with us. So her presentation entitled with preparation and characterization of zinc oxide-based Schottky diode prepared with sol gel method. That's right. So, please share your presentation. okay. Please.
Yeah.
Just let me check, please.
Yeah.
It's okay.
So, good morning, everybody, and welcome to my presentation. The topic of my presentation is preparation and characterization of zinc oxide based shotcrete diode prepared with Sol-Gel method. Okay, so first of all, I am Arab Visa. I am from Algeria. My university is the University of Biskra. So this work was carried out with our students of master in the laboratory of metallic and semiconductor materials at the University of Biskra. Okay. So, okay.
Maybe you can use
Keywords.
please.
Okay. This one.
This maybe.
Yeah.
It's useful.
Thanks. So, in this presentation, I will focus on the aims of the studies. Second, generalities about the zinc oxide. Then I will show you the different experimental steps followed in these studies. A large part of this presentation will preserve the results and discussion. I finish by conclusion where I highlight the main results obtained. I finish by some outlook points. So, our work leads to the elaboration and optimization of zinc oxide thin films, pure, doped with gallium, co-doped with indium and aluminium, using the Sol-Gel method and disposited by spin coating. The optimum films have been used in fabrication of Schottky diode, which is our application of this study. So we start by some generalities of zinc oxide. Zinc oxide is a transparent and conductive oxide, TCO. Its conductivity due to the presence of an excess of electrons created either by structural defects or appropriate doping. It is a semiconductor N-type. It is very stable chemically with high luminescent efficiency and non-toxic with weight band gap, which is 3.37 electron volt at room temperature. So, zinc oxide can be crystallized in three structures. We have this one, which is blend zinc, but it is a metastable structure. This second one, which is the rock salt structure, it's the structure of the sodium chloride, which is a salt. The third one is the weird structure or hexagonal structure of zinc oxide, which is the most thermodynamically stable. Here we have some characteristic or parameters of this, the last one, which is the structure, what our film our films will be crystallized. So, zinc oxide is found in many applications. We have here antimicrobial. We have also photocatalytic activity, cosmetic and gas sensor, varistors, and agriculture. Well, now we go to the experimental part. The preparation method adopted in this study is the Sol-Gel. It is the abbreviation of solution gelification. So we have transition between sol to the gelification, the aspect of this material. It is a chemical method and the most extensively underscore extensively, not expensively, extensively used technique for producing zinc oxide nanoparticles because of its good homogeneity, simplicity of composition control, low processing temperature. We work in lower temperature. So, large area of coating. We can use this method for coat a large area. It is a cheap equipment cost and excellent optical. It has excellent. We will get an excellent optical qualities for films. The films will be deposited by two processes or two techniques. We have deep coating, this one. This is the substrate. We will immerse it in the solution and get our film. And the second one or the second technique is the spin coating. We have here substrate, good of our gelification, our gel, and we have rotation and to get at the center our film. So this slide presents the different steps, experimental steps followed in this study. We start by cleaning our substrate in ultrasonic bath. We have used methanol, acetone, and distilled water. The master precursor used is zinc acetate dihydrate. It is the precursor of zinc oxide. We have used ethanol as a solvent and diethanolamine as stabilizing agent. The solution was stirred at 60 degrees Celsius for 30 minutes. For thin film of ZNO dopant, we have used nitrates of aluminium, indium, and gallium as a source of aluminium, indium, and gallium. The solution was left to rest for 24 hours or for 8 days. Before depositing our layers, we have used the spin coating technique, this one. Each layer deposited was treated thermally at 5 degrees Celsius for 30 minutes. And to get to films of zinc oxide, we must repeat this step, the last step, which is depositing layer, for 7 times. At the final, the films of ZNO was annealed for 30 minutes at 500 degrees Celsius. The substrates used in this study are A2 substrates and glass substrates. For diode, zinc oxide diode, we have used the substrate of A2, deposited zinc oxide doped with gallium, and the next one, the next film, is the zinc oxide co-doped with aluminium and indium. The characterization method adopted in this study, we have used X-ray diffraction, UV visible, and we have used for electric properties, we have used EV and 4 quench. This 4 quench and this one, it's EV. Now, we go to the result and discussion. So, this figures present the X-ray diffraction spectra of ZNO spin films deposited on E2 substrate. The first figure is for ZNO and doped, and this one for ZNO doped with gallium, 8%. And the third one, ZNO co-doped with aluminium and indium. Each one we have 40%. We notice that all symbols present on hexagonal weighted structure of ZNO. This indicates that doping with gallium, aluminium, and indium don't fundamentally change the structure of zinc oxide. We can say that we have a solid solution. Peaks marked with asterisk are peaks of the A2 substrate. We have here this second figure and for third figure. All these peaks are concerned to A2 substrates. So, the present table shows the variation in crystal size, depth, and strain, and dislocation density for different films elaborated. We have here zinc oxide and doped with gallium and co-doped with aluminium and indium. This variation is clearly shown in this figure. For the curve with black color, we have the variation of the crystalline size. We notice that we have lower value of crystalline size for zinc oxide co-doped with aluminum and indium, which is 19.973 nanometers. For zinc oxide undoped, we have recorded the crystalline size 37.875 nanometers. However, for the dislocation density, the blue one, and the strain, red one, we have recorded a high value for zinc oxide doped with gallium and co-doped with aluminum and indium. This result is clearly correct because we have some defect in these films, which are the doping atoms of gallium and aluminum and indium. Because this results for results of crystalline size confirm that we are in now scholar issues. So, here we present it's an overview of UV visible results. For the first figure, here we have optical transmission spectra of zinc oxide thin films and diode deposited on E2 substrate, where the solution used was left to rest for 24 hours. Here we notice that all samples have a high transmittance, over 90% in the visible region here. And while we have almost complete absorption in the UV visible. The second figure presents it is a comparison between the use of E2 substrate and glasses substrate. We notice that the two kinds of substrates show a high transmittance, and the choice between them it should be aligned with the application intended application of these films or this diode. The third figure shows the optical transmission spectra of ZNO oxide thin films and the diode. Here we have used two solutions. Here we study the effect of times. We have used the solvents that used after the solvent were left to rest for 24 hours, and here we have 8 days. For zinc oxide, this color and this one, the green, we notice that there is some degradation in the quality of the ZNO films. However, for diode, this color, we can say blue color, and this one, orange, this diode keeps the same characteristic. We have not most change in this characteristic, the characteristic of the diode. It's an overview. This result UV visible underscore overview of transmittance of zinc oxide thin films, and we have must study the effect of the choose of substrate and the stability of the solution that affect the performance of the films of ZNO or of the diode. So here we have figures that shows the variation of gap energy and Urbach energy for films that deposited on E2 substrate and on glass substrate. On E2 substrate, we have recorded a lower value of disorder, red one, lower value for zinc oxide doped with gallium, which is improved the quality of the films. However, for ZNO co-doped with aluminum and indium, we have a higher value for the disorder. For the gap, it's logical. We have recorded a high value for gap energy, also for zinc oxide doped with gallium. So, the lower value of the gap is recorded for the doped with co-doped with aluminum and indium. This for substrate E2 substrate. For glass substrate, here we have that we notice that for zinc oxide doped with gallium and co-doped, we have recorded a lower value for the disorder energy, which improve the quality of this film, and a high value for energy of the gut. So this table summarizes the value of the sheet resistivity, this one, and the conductivity and the resistivity for ZNO and doped. We can't say pure. It's logically we say and doped. There is no zinc oxide pure, and ZNO doped with gallium 4% and co-doped with aluminum and indium. Here we study just only the films that deposited on glass. Because if we study the films that deposited on ETU glass, we can't get the resistivity of the films because ETU has high conductivity. So the figure shows the variation of these parameters. Here we have red color, the conductivity. We have recorded a high conductivity for the ZNO co-doped with aluminum and indium. And this result, it is very important for our study for the diode Schottky. EV characteristic. Here we have the current voltage characteristic of the diode symbol in the linear scale. This one we have used an old solution, which is solution that was left to rest for 8 days, and here for just for 24 hours. The comparison between the two figures don't show slight difference. We can say that EV characteristic confirms the result that obtained with UV visible. That we have said that for diode there is no difference between the use of a solution used left to rest for 24 hours or 20 days. The diode keeps its characteristic. Here we have we can say that we have Schottky behavior, okay, not linear variation of the current with voltage. And here we have the blue color with our diode is under light, and the red color is in darkness. We can't remark that there is there is no difference between the two conditions. Maybe you can use the strong light, remark or record some differences between them. So, from the last characterization, we can detect resistance series, idle factor, and saturation current, and the barrier. Even for the new solution, the solution was left to rest for 24 hours, and here for 8 days in darkness and lightness. As we say, there is no strong difference between the results. So we finish by conclusion, where I highlight the main results obtained. The study involved the fabrication and characterization of n-doped and doped zinc oxide films for ZNO in the goal to get zinc oxide-based Schottky diode. The film includes gallium doped zinc oxide 8%, co-doped zinc oxide with aluminum and indium. For each one we have 4%, and doped zinc oxide. This film were prepared using sol-gel deposition on E2 and glass substrate, resulting in 7-layer diodes with a total thickness of around 8%, 50 nanometers. Key finding results include that all films exhibit on polycrystalline hexagonal structure fast character. Energy band gap value for the films deposited on E2 substrate are 3.25 electron volts for n-doped, 3.27 electron volt for ZNO doped with gallium, and 3.1 electron volt for ZNO co-doped with aluminum and indium. The films and diodes show high transparency, over 90% in the visible region, and high absorption even. electrical resistivity value for doped and co-doped zinc oxide film are decreased compared to a-doped zinc oxide, as we show this value, respectively. The diode display Schottky tip behavior. We have a Schottky behavior in dark and light conditions. The key parameters such as barrier height, ideality factor, and series resistance were derived from EV characteristic. And I finish by some outlook points for this work with several potential direction and application. Further, maybe you can study the doping studies effects, exploring different doping elements and concentration to further improve the electrical and optical properties of zinc oxide films. Layer thickness, we can play on thickness of the layers. And performance metrics, focusing on improving field performance metrics such as the barrier higher, ideality factor, series resistance, and to enhance the efficiency and reliability of the diode, delivering the high transparency of the films for use in transparent electronic devices. Thank you for your attention.
Is there a question?
Yeah.
Yes.
Okay. Okay. Why this one? Yeah.
There is two
Yeah.
graphs. Probably the energy Iraq.
Okay.
And then
I got-
Gallium, we can see that gallium as ability. The energy Iraq is shifting down.
Yeah.
But when you drop it with aluminum,
Code of with indium and aluminum. Yeah.
is the energy left in the gap when the deep level take place.
We have some defect in the gaps.
In the gases form.
Okay.
So I can see that gallium doesn't affect the gap. As we can see at the same point, the gap is how to say
Large, yeah.
enlarged. It has to enlarge the gap. It's a good how to say, it's good doublet, but the good doublet.
Yeah.
Aluminum. What's mean doublet and doublet?
We use two types of doping. Co-doping. It's at the same time. Yeah.
The atomic doublet.
Yeah.
But here with the aluminum and indium, I think another further work on
Yeah.
how to say.
Maybe outlook. Yeah.
Maybe aluminum with gallium. Aluminum with gallium, it's already a winner existing,
Yeah.
and it has application in the transistors.
Yeah.
But here, aluminum is affecting negatively how to know which atom is affecting the gap. Gallium is enlarging the gap. Aluminum with indium is shrinking the gap. So which atom is
Do you mean
affecting the
which atom, aluminum or indium? Yeah.
Yeah.
We can
Gallium-
say
gallium-
which atom. We can't
gallium-
precise which atom because you have used the same at the same time. We have used aluminum, and maybe it's another study.
Yeah.
Yeah.
It's why I said aluminum only, indium only, or aluminum with gallium, or aluminum with as binary.
Yeah.
Yeah, because here it's gallium, only gallium is enlarged the gap, and aluminum with indium is
We can say that's just only the aluminum. We have here aluminum and indium. Okay. Yeah, it's binary. We can't talk about just one doping element. Yeah. We have two at the same time. Okay? It's a study similar to metal insulator semiconductor junction. We have we didn't use the insulator, we used materials that have a high resistivity. Instead, the insulator. Okay? Okay? It's clear?
Yeah.
Did I answer your question?
Yeah.
Okay. Another question?
Thank you so much.
Another
Welcome.
question?
Okay.
No, okay, let me ask a question,
Okay.
please.
Of course, please.
Can you come back to the UV results, please?
You do results, yeah.
And sorry for that, I didn't catch the film thicknesses.
What?
What is your film thicknesses?
Film thicknesses. Okay. Maybe I mentioned it at the conclusion. I didn't precise the film thicknesses here. Okay.
Okay.
Yeah, at the end we have the thicknesses of the diode is 8%. Our diode, which is the
Sorry, you prepared some zinc oxide and doped and coated zinc oxide fittings on the ITO and glass substrates.
Okay, it's clear.
Okay. I asked the thickness of the zinc oxide or coated zinc oxide thin films. 100 nanometer, 100 nanometer.
We repeated for each films, we have repeated the depositing layer for 7 times. And at the end, we have that, for example, for the diode, we have that the thickness is 8%. Sorry, we get to the end. The diode. And we have repeated the same depositing films for each one 7 times. We can say that we have almost 300 nanometers, yeah, for each one, yeah.
Because it's a problem here, are in the same lab. She's in team and in another team, and we don't have the equipment to measure thickness. It's the real problem for me.
No, for this, it's a student, master student work. We didn't precise the work exactly, and
you don't have profile micrometer, I think. You don't have profilometer.
Ellipsometer.
No, not ellipsometer.
Yeah.
Profilometer.
In general,
they can do it. They can measure the thickness, but not that exactly.
No, the profilometer.
It's a very important parameter, as he said. The thickness is very important parameter. Yes, in general, in our university, how we do use the map, the SEM characterization. We put the film like this. Yeah, and we measure our thickness.
Okay. So one of my other questions.
Okay.
Is,
yes.
UV results again, please.
UV results. Yeah. Okay.
Do you have any substrate?
Sorry, just return to your first question. We can measure here the thickness of the films by using the French here. There is a relation,
yes, it's a way to calculate the thickness.
Yes, it's a method, yeah.
Before my last question, I support my before sentence.
Yes.
The profilometer is a mechanic way to measure the thickness of thin films.
But sorry.
At tip, you know, at tip is more.
I know it, but it is not very precise for in the nanoscale.
Okay.
Yeah. The preference we use the SEM or ellipsometry. For nanometer scale, it is not this method, this technique is not really precise.
Okay.
Yeah.
I don't know if you have any samples with you. You can measure it here. And
sorry, I didn't bring me.
Okay, we can contact after.
Inshallah. Okay, inshallah. Okay.
My last question.
Okay.
How did we or you get the transparency value above the 100%?
Here.
At the visible region, especially.
Here we can say that there is some error because it is not logic to get more than 100. There is some error about the technique or how to say
Can we say it's
for this
measurement error maybe?
error maybe, yeah. It is not logic to get more than 100, yeah.
I think, yeah.
Yeah.
Okay.
This is a narrow instrument error.
If it's
Yeah.
measurement error, okay, but
Yeah. It is not
you know that
impossible.
there is no other logical
Yeah.
result for that. Yes.
Yes.
Okay, thank you very much.
You're welcome.
Lisa, again, please.
Thank you. Yes, please. Thanks. Yes.
Okay, well, thank you again, Lisa, for your presentation. I will give you welcome. So, our next presentation from, yes, what's the problem?
Hocam öteki
Okay,
ekranıydı.
okay,
Windows ne
okay,
yapıyordu?
okay,
Windows
okay, okay, okay.
Windows P'ye
Don't worry, okay.
Ha, tamam. Yine yapacak.
Okay. So our next speaker is Dr. Mahmut Bucugat from Gazi University, Turkey, and his presentation title, Elimination Effect on Capacitance Voltage Characteristic on Negative Capacitance Behavior in MS and Mistype Structures, I think. Welcome. Welcome. Yes. Please. I will open your presentation.
So it's no need to enlarge, so
It's okay. What?
Okay, I'm Mahmut Bucugat from the physics department of Gazi University. I'm going to talk about the elimination effects on the capacitance voltage characteristics and negative capacitance behavior in metal semiconductor and metal insulator structure, metal insulator semiconductor structures. Here, the semiconductor is the N-type gallium arsenide, and the insulator is the silicon nitride. Here, silicon nitride is on the primary role, so I'm going to give a brief property of the silicon nitride. It's used in the industry, a known material. It's used in the automobile industry, especially in engine parts and bearings, because of its durability to high temperature. And it's harder than a metal because it's a ceramic structure, and it has also applications in medicine, especially in orthopedics. It's used as implants in orthopedics, and as it's a harder material, it's used in metal working, especially in metal cutting works. And of course, it's used in electronics too, because it's an insulator, and it's used as an insulator and chemical barrier in manufacturing integrated circuits, because it has a high dielectric constant. It has about 2 times larger dielectric constant than silicon dioxide. So that's why we chose it as an insulator in our capacitance measurement. And it's also used in solar cells to use it as anti-reflective coating in the solar cell windows. Here, this is the simple sketch of our device. Here we used an N-type gallium arsenide as an substrate, which has a thickness of 380 micrometers, and gold is covered on the backside of the gallium arsenide as ohmic contact, which has 200 nanometers thickness. And at the upper side of the gallium arsenide, silicon nitride layer is grown with 15 nanometer thickness. And at the very top of our device, there are gold and titanium layered Schottky contacts. Here, the layers are grown with the atomic layer deposition technique. And this is the simple schematic diagram of our experiment. Solar simulator is used as a source of illumination. The illumination intensity is 100 milliwatts per centimeter square. And of course, there is an impedance analyzer. We made the experiments under 1 megahertz frequency. And of course, there is the computer system which takes and store the data. And these are the capacitance voltage characteristics of our measurements. Here the measurements are done from -2 to +2 voltage range for both structures. On the left-hand side, there is the metal semiconductor type structure, and on the right-hand side there is the MIS metal insulator semiconductor type structures. Capacitance voltage results are given. Here, at first sight, when we look at the graphs, we see that the three regions, inversion and depletion and accumulation regions, are clearly seen on the both graphs. And again, at first sight, we see that the capacitance goes to an upper value, and it shows a tendency to go to negative values in both graphs. And of course, we see that the illumination has a positive effect on both graphs, on both in the inversion and depletion regions. But on the MIS type, it's seen that the light has too little effect on the capacitance values. And the tendency of the capacitance going to negative values, and the negative valued capacitance is called negative capacitance in the literature. And gallium arsenide is a well-known material which shows negative capacitance. Here, of course, we can talk about the effect of interfacial layer in the capacitance effect of the device. And the interesting thing is we see peaks in the MIS type structures capacitance voltage values. These peaks may be due to the surface depolarization and series resistance of the device, and because of the insulator layer between metal semiconductor interface. And there is also the shifts on both graphs, and these shifts may be due to the spatial distribution of density distribution of the surface states, and we can say that this may be due to the lifetime or the relaxation time of the carriers. And moreover, the reorder and restructure of carriers under illumination. And we see that again, the light has no effect on the accumulation part of the MIS type structure. Surface states are important in the capacitance values of a device. So here there are the surface states, density of surface states graphs for both structures. This surface state density with respect to voltage graphs are obtained with the method, which is the difference of capacitance in dark with capacitance in illumination. So the equation is a very clear equation to calculate the capacitance, to calculate the surface states. And when we look at these graphs, we see that there are again peaks in both type structures for surface states in the positive bias region. And we again see that the peaks shift towards to the higher values of positive voltage in the MIS type structure. And we also see that the surface states decreases about 10 order in MIS type structure. Now, when we talk about the negative capacitance property, in literature, there are various studies about negative capacitance. And authors say that negative capacitance is different for different electronic devices. And authors again say that NC can be observed for different frequencies and temperatures. For example, one of the research groups say that this negative capacitance can be caused by the inductive behavior of the material, so that the conductance starts to increase and capacitance decreases. In another research, authors say that this negative capacitance can be caused by the injection and relaxation by minority carriers and surface states. And there is an interesting research result saying that the negative capacitance or the negative dielectric behavior is the result of instrumental problems. So there are various explanations for negative capacitance, but as a summary or totally, we can say that the negative capacitance is attributed to the surface states, relaxation times of surface states depending on frequency, and the series resistance of the device. And finally, it can be said that minor carrier injection can also cause this negative capacitance. And we can explain negative capacitance with the basic capacitance equation, which says that the change of charge with respect to changing voltage gives us the capacitance. And here we can say that the capacitance goes to negative values when there is an increase in the charge number, which leads to a decrease in voltage, or vice versa. We can see negative values of capacitance with respect to the changing of charge or voltage. Now, in our present case, we can say that it's, first of all, we say that surface states play an important role in negative capacitance. But in our present case, we see that surface states decreases with increasing positive bias values. And it's also known that surface states are effective at low frequencies. And in this study, 1 megahertz frequency is used. So we can omit the effect of surface states in the negative capacitance behavior of this device. So other choices are the series resistance, which is caused by the contacts and interfaces, because we used two Schottky contacts, aluminum and titanium contacts for Schottky contacts. And interfaces, of course, may play important role in the negative capacitance. And finally, the minor carrier injection, maybe this is the highest possibility, saying that the effective charge decreases in the depletion layer. So this causes the drop of capacitance of the device. And moreover, we can obtain some electrical parameters from the measurements in the linear parts of 1/, capacitance square versus voltage graphs. We can calculate the Fermi energy, the thickness of the depletion width, and the barrier height and doping concentration of donor atoms. These are the numerical values calculated from these two graphs. Here, overall, we can say that the Fermi energy and doping concentration of donors increase under illumination in metal semiconductor type structure. However, barrier height and the depletion width decreases under illumination, and in MIS type structure, only doping concentration of donors increases, and the other parameters, Fermi energy, the barrier height, and the depletion width decrease. In fact, it's the effect of light can be seen in these parameters, and some of them are expected results for the increasing and decreasing of these parameters. As a first conclusion for the electrical parameters, the calculation method may affect the results. So when we use different calculation methods, the results can slightly change with respect to the method. And these parameters may change again with the effect of the surface state density due to the insulator layer. And again, we can say that the series resistance due to contacts and interface can also change these parameters. And finally, we can say that the barrier inhomogeneity in the metal semiconductor junction can also affect these parameters. Here, in this case, we can say that the negative capacitance may be attributed to high-level injection of minority carriers from the depletion layer to the semiconductor. Again, loss of interface charges or interface states localized between metal and semiconductor due to impact ionization process, and again, because of the serial resistance of the device. And the conclusion for the effect of light on negative capacitance can be the effect of illumination might passivate the traps, and so that the surface state density decreases. And in the graph, we saw that the illumination has no extra effect on the negative capacitance in the MIS type structure, but it has a distinct effect on the capacitance of the metal semiconductor type structure. And the general conclusion is the high dielectric constant interlayer silicon nitride usage leads to improve the performance of conventional metal semiconductor type diode in respect of its high barrier height and low surface states. So it can be used in the production of diode devices. So thank you for the attention. That's all.
Thank you very much, Mr. Gülben. So is there a question? You?
Yes.
Okay.
Hello.
Hello.
See, what you used to measure the
I used the HP impedance analyzer here. If I find it, let me show it to you. This is the real picture of our device. This device can be used for both measuring the capacitance and the conductance of the measuring device or the measured device. So we used this analyzer in the measurements.
The contact you have. How do you do the contact to measure?
We have two contacts.
It's a big surface.
No, it's not a big surface. We only take one of the aluminum titanium contacts there. I put there many of them because you know when you produce a diode, you prepare many devices. So there are more contacts here. I only used one of the aluminum titanium contacts, the gold titanium contacts there. The yellow cylinders are single contacts. So one of the contacts goes, for example, that yellow Schottky contact, and the other one goes to the negative side of the diode.
For the frequency, how did you make the relationship with the frequency after that?
Here?
No, when you talk about frequency, it's 1 megahertz something after.
After here.
After, yeah, after now.
Here, I have only two type of graphs here, only CV and the surface state graphs here. Of course, this is the preliminary results. We have other measurements about this. There are measurements with different frequencies in.
From the figures of the capacitance, you calculate the frequency. It's 1 megahertz.
No, I didn't calculate it. It's the frequency given or applied by the device to the sample.
Okay. I thought you calculated and then.
No, it's you can measure the capacitance with respect to changing frequencies. So I only gave here 1 megahertz result. Of course, there are other results with respect to different frequencies. The capacitance changes with respect to the applied frequency.
Thank you. Okay.
Okay, thank you.
Again, thank you very much.
Okay, thank you.
Okay. Oh, so our next speaker is Şenol Gülgönül, and he isn't here, I think. Maybe we can wait for a while, our speakers, and we will come back again. Thank you. Hello, Mr. Ismail Taşçı. Can you hear me? Mr. Taşçı, can you hear me? Hello, again. Okay. So, dear participants, we are finishing our session. Also, we are finishing the conference for the whole C, excuse me, whole B. And we will start the Zoom meetings. So, good day for everyone.